Hello everyone, I'm Dinesh. I'm a senior researcher and manager at IBM Research. So I will cover 6 lectures on AI agents. So to begin with, I'll go back to how this particular field started, where it started, and then we gradually move towards where it is now. So probably in the 5th, 6th lecture, we'll talk about more recent things, but until then, we'll cover the basics to understand why we are here in this field. So before going into AI agents, I'll just briefly introduce my team at IBM Research. So we are a team called the Conversational AI group. We have 2 main streams of work in our team. One is around agentic AI. How do we it covers both how do we train LLMs for being better agents till how do we develop good AI solutions for agents, right? So it covers the entire spectrum. There are a lot of people in the group. And the second set of people in my team, they work on retrieval augmented generation. Again, there are multiple aspects of RAG which Yatin might have covered in the previous lectures. And our team works on a few of those aspects. So Gaurav in our team, he primarily was focusing on post-training techniques, specifically alignment phase of large language model training. And now recently he has shifted that focus of not just doing it for reasoning and general purpose in alignment, but rather how can we use RL techniques to improve AI agents, right? So yeah, so this is an overview of the team. Now let me get into the basics of the agentic AI. So the most crucial component of an agentic AI system is its ability to call external tools, basically to use non-parametric. How can it leverage non-parametric knowledge in the whole decision making and overall response generation to the user? So let's go back to sort of like a year or two ago where LLMs did not have access to tools, right? So so everything the LLMs did were based on what they had in their parametric knowledge. So during those times, when say you ask a model about a question about a current event, like who is the current president of India, so then the model is most likely to answer based on until when it was trained, right? So for example, Mistral 8x7B model, when I queried it last year, it said that based on my last update, the current president of India is Ramnath Kovind, and it also gives you a disclaimer that he has been in office since this time, and this may not be reliable, and you'll have to verify it because there may be latest changes to this information, right? So it can only give you a disclaimer, but it can't actually solve the problem at hand. So of course the obvious solution to this is that as humans, we use search engines and then go through multiple links and then figure out where the answer is contained, and then we sort of understand what the answer is. Similarly, LLMs were also given access to search tools, and the way they work is that if you see how ChatGPT works, when the question is more time dependent, or when ChatGPT feels that it won't be able to answer this question from the parametric knowledge and it's better to access other websites, then it would sort of invoke the search engine or the search tool. And if you see the first 3 parts of how it got to the answer, it has created a query called current Prime Minister of India, October 2024, based on the time I called it. And then based on that search result, based on using Bing search, it sort of got many results, and then it clicked on these 2 results, and based on these 2 results, the model has generated the response, right? So this is how LLM is able to use external tools to sort of augment its parametric knowledge and then give answers to questions which it feels cannot be answered just from parametric knowledge. Similarly, another issue with LLMs was that even though they were really good in language-specific tasks, they achieved superhuman performance in language-specific tasks, they sort of fail many times on very simple reasoning and math operations, right? So one example here on a Llama 2 13 billion chat model was, if you multiply a very small number, 3 with a 7-digit or 8-digit number, then it ends up hallucinating a lot. So even though there are only 8 digits in the resulting answer, it ended up generating much more than it makes mistakes at that level, right? The order of the result is like much bigger than what it should have been. And imagine that using this for banking solutions, right? If you want to transfer like 2,000 rupees and it ends up transferring 2 lakh, right? So this is a big issue. Like even elementary mathematical skills are not good in LLMs, right? And of course, an easy technique would be to use calculator or Python interpreter or any other deterministic way of computing simple math equations, right? And that's exactly what ended up happening. So if you query ChatGPT with any such queries that requires mathematical calculation, or in fact you might have also seen this on Google search, right? So if you query with a mathematical operation, it'll show you the output in a calculator rather than a web search result, right? So that's exactly what people who work with LLM also did, which is they would give you the answer by using a Python interpreter, right? So if you click on this particular tooltip, it will show you what it did, which is like it created this particular Python program, and the result was then used for generating the final response, right? So this is another example where a tool can make it solve a problem that LLMs are not good at, right? So let's summarize. So why are tools important? One easy example that we took was a web search tool where it helps overcome LLM over its knowledge limits. Two is it can have accurate reasoning and computations that can help you solve like math problems or any other related reasoning problems. You can use Python functions or some APIs that can help you do math problems and things like that. But why is this very important, right? So let's see like a slightly more real world use case, right? So let's say that you're in an enterprise setup and you likely have a lot of knowledge in your database, a lot of knowledge stored in multiple sectors in your org, and most of these APIs and data is not available out in the public, right? So if you ask questions like show me the top 10 customers by revenue this quarter, so then there's no way for the model to answer this question unless you provided access to the APIs which can help you get these data, right? So having access to tools is very, very important to solve real world questions, right? So let's say that you call Airtel or Jio customer care and then say that my last bill is too high. I don't think that I've used this much data or I've called these many people. Can you check why this issue is? Of course, if you have to automate something like this, the model first has to understand who you are, fetch relevant information, understand the guidelines of how bills are generated, and should be able to answer, right? And these are not in the public domain. So most of these tools will be available to you in enterprise system, but the model should be able to leverage these tools along with its ability to converse with people, right? And slightly more like complex use cases, like let's say you're building an autonomous agent that can automatically create PR in your repo, right? And you want to create such an autonomous bot within your organization. Then it has to know all the code in your private repo. It should be able to call an LLM with some parts of this repository, figure out like what is a problem, understand the solution, and come up with a solution and create a PR, right? And of course, like the code for your particular use case may not be available in the public domain. So there's a lot of knowledge and tools that enterprise have or other organizations might have, which LLMs would not know in general. And that's exactly where tools are very important. And that's why understanding tools is so critical for LLM agents. Otherwise, you cannot automate any use case that you have in mind, right? So with this in mind, like eventually after the 6 lectures, you will be able to appreciate how much the field has moved towards building autonomous agents, which can use tools to solve complex real life problem. You will also be able to understand where all they still fail and where work is needed to go forward, right? So So I've divided the lectures into three parts, and in the first part we'll just talk about how this whole field of using tools with LLM started. So we will go through very like innovative papers, 4 or 5 innovative papers in that field to understand how they started this field, and then we will move on to where the field is now and what is the acceptable norm in using external APIs, like how do, like, let's say Mixtral or Claude or GPT models allow you to give them specifications of tools and they will leverage in their workflow, right, in building agents. And finally, we'll talk about is it just tools that are needed to get going, or what other complexities are involved in actually building an agent, right? Tools are essential part, but they are not sufficient, right? So what are those? And then we'll get into some use cases. We'll understand what are the issues and then what are the problems that are still open in this particular field. So I will be covering part 1 in this lecture. Part 2 will be the next 2 lectures after that, and part 3 will cover the last 3. Right? So the term that I'll use is that just to understand how tools are used in LLMs, specifically during the post-training phase. Like you already have an instruct LLM, then how can you make use of tools is what will be tool augmentation. Second is like while you create the instruction fine-tune model, or when you create the instruct model, how can you infuse the ability to access external tools, right? That's what we'll cover in part 2, which is called function calling or tool calling. And in the third part, of course, we'll cover the broader spectrum of how to develop AI agents. Okay, so the outline for today's talk will be that I'll talk about one of the first works that talked about tools and LLMs. This was by OpenAI, and it's called like solving math problems using a dataset called GSM-8K. Then we'll talk about 2 other papers that helps augment tools into the fine-tuning process, and then we'll talk about Toolformer, which goes slightly above instruction fine-tuning and says that how can we in general make LLMs aware of like a set of tools that you have at hand so that it can use it in any task that it can solve. And if time permits, I'll also talk about WebGPT. This is the like in the example that I showed about who is the current president or prime minister of India. It sort of did how a human did, right? It'll create a search query, figure out, like go through the search results, understand what parts make sense, and then summarize it. So this was the first paper that talked about how you would methodically do it, or what type of data do you need to teach LLMs this ability. So if time permits, I'll cover that, but otherwise it's a good paper to read otherwise. Okay, so let's start with GSM-8K. So GSM-8K is a math dataset. It's grade school math word problems. These are not very complicated. These are quite simple problems like Beth bakes 2 dozen batches of cookies in a week. If these cookies are shared among 16 people equally, how many cookies does each person consume? So these are going to be problems like these. So the reason why this dataset was important was the datasets that exist previously were either too complex or too simple. Too simple in the sense they were all templatized, like in the sense that they may just replace some numbers or some words here and there, but in general they follow a very standard template. And so those datasets were, studying those datasets were not really exposing the problems within LLM, or they were too complex, right? And here the answer is quite straightforward. It's an integer, it's easy to measure, it's easy to evaluate. So, but all the problems here are human written. They are not like crawled from any website. They are not systematically synthesized using either templates or LLMs. So these are human written ones. So the diversity of natural language is very high. And the answers are mostly right. So the paper claims that they predict that only there will be less than 2% noise in the data set. So it's that clean, right? And what they showed is that the paper came in 2011, 2021, and at that time GPT-3 was the state-of-the-art model. And what they showed is that on this very simple grade school math problem, GPT-3 175 billion model was only doing about 20% accurate, right? So there was a big gap to be bridged, but they were doing very good on a lot of natural language tasks like question answering or squad like data sets, right, or reasoning data sets on text. And similarly, smaller models like 6 billion model was even worse, right? So the goal of this paper was to showcase this issue, that they are not good at very simple math while they claim to be really good otherwise, right? And also study how can we improve them, right? That's the other thing. So when they asked humans to create this data set, they also asked them to not just write the final answer, but rather give step-by-step explanation of how to arrive at the answer, right? So you can see those examples here. In addition to this, they also said, they also asked them to do some sort of tool annotations. In this context, the only tool that they have access to is something like a calculator, and they only support basic math operations like addition, subtraction, multiplication, and division. That's about it, right? So this was the instruction given to them. So they basically annotated this part, right, which is in order to get to 8 dozen cookies, and I have 4 and 2 in my input, so it's 4 into 2, which is equal to 8. And so they did all these annotations. So let's see where these annotations are useful and how they help model get better. So first, one thing to understand is that in this problem, they are considering a scenario where you have a GPT-3 model, be it 6 billion or 175 billion, and your goal is to make it work good only on GSM 8K, right? They don't worry about okay, if I fine tune, will it regress on other natural language tasks, right? Because of course, if you fine tune it for this specific task, the model is going to work only for that. So the current goal is just that. Let's not worry about other tasks. Let's assume after I fine tune this model, it's going to be used only for this task, right? Well, this is a big disadvantage, but it's anyway a good study to understand the problem, right? So the way they fine tuned this was slightly different compared to the usual technique. Like usually, what would you do? The problem would be fed as input, right? And then you would use either only the final answer as the output, or you would use solution plus final answer as the output, right? This is the typical way people would have fine-tuned, right? So, but they did not do it that way. The reason being that this was different compared to what typically you would have. So they wanted to use it to their advantage, right? And the reason why they went for this annotation to begin with was there was a study before which said that LLMs are autoregressive models, and all the model has to do is make one mathematical mistake in the solution for it to fail completely, right? It's a single point of failure, right? Once it fails, then it's going to cascade the error and it's going to blow out of proportion, right? And LLMs at that point in time were not good at even single digit arithmetic, right? So that was the reason why it failed. So and specifically the part where 8 was predicted from 4 and 2, or the part where 96 was predicted from 12 and 8, or the place where 6 was predicted from 96 and 16, right? It's at these points that the model failed. So what this paper tried was, okay, maybe let's use a tool to do this job rather than let the LLM do it, right? So that was the goal. So what they did was, until this point, it is typical LLM next word prediction training, right? You give the entire input and you let the model predict the next word, right? So once you have, let's say, 2 angular brackets and 20, it's going to predict plus, and then it's going to predict the number 10, and then it would predict equals, right? So the moment LLM predicts equal, they are not going to have the next token prediction trained for the LLM. What they would do is, they would take the content after the 2 angular brackets and everything after that till equals this part, sorry, right? And they will use a calculator to evaluate that expression, and they'll directly put that number 30 and the close angular brackets into the LLM input, right? So this part is never trained. This is never trained, right? So which will ensure that the model will never go wrong in this particular token prediction, right? And the only change that they have to make is, instead of saying equal to 30 directly, they are going to, the model has to learn to not predict the output by itself, but rather just generate the expression for which it needs the output. So that's what you're teaching the LLM, right? So let's see what happened, right? So now, because of this new fine-tuning strategy, the model started to, this is a 175 billion GPT-3 model. The model slowly started to improve as and when you train. But the issue is like, they only had collected 8K data points, right? And so there were some used for validation and testing. And this just helped improve 10% of the performance, right? And at this rate, which you have to, let's say if you have to reach 90 or like acceptable performance on math, you need insane amount of data, right? So then the part comes like, how do we improve this further with the limited data that we have, right? So what they found was that, so this is the setup where you would just do inferencing with temperature equal to 0, which is basically greedy decoding, right? So you take one sample and then you check what is the accuracy of the answer. So like I said, after they trained it, so this is a 6 billion model, not a 175 billion model, so the performance will not be 30 after 8K, but rather after training over around 50 epochs, they were only able to achieve around 22% accuracy, right? On the other hand, what they did was they set the temperature a little higher, right? Which means the model can now generate slightly more variations and also get out slightly less probable output sequences. And then they sampled 100 samples, right? And what they saw was, like even before, even slightly after the training started, it was around 78, right? Which is good. But then what they noticed is that unlike the overall greedy decoding accuracy, the percentage of cases where the answer was in one of those hundreds kept first increased a bit and then start to decline rapidly, right? So the reason, so can anybody guess why this is happening? You would expect this to go high, right?
Because there should be a time.
Okay, so that's a good point. So you're saying like maybe temperature being at 0.7 could be one of the reasons why this sort of trend is happening, right? So anybody else? Any other guesses? That's a good point. So how many of you have fine-tuned an LLM for a specific task at hand for them? Have you tried fine-tuning an LLM for a very specific task? Okay, so what typically happens with very specific tasks, right? You will start to forget everything else in the world and focus only on this particular problem at hand, right? And let's say you hit a point where you can't learn any new patterns, right? If you can't learn any new patterns, what would you do? The objective function says that increase the log likelihood of the right token, right? So what it would do is it will spend all its energy to reduce probability mass on other tokens that are not right and put all its energy on just one token that is right. So what happens, the distribution becomes a lot peaky, right? So it starts to get more and more confident on just the right answer. So its ability to explore reduces, right? So when you use a temperature of 0.7, of course, the second one has to be somewhat higher for you to get sampled to begin with, right? So basically what happens is that if you train a lot, then the diversity at 0.7 would not be good. So that's exactly comes to your point, which is maybe if you change your temperature from 0.7 to slightly higher, maybe it might have chosen even lower probable ones, and that could have helped. But that's what happens here, right? So what they did was that they took a lot of samples from this particular stage of training, right? So they know that around 84% of the times one of the answers is right, and of course they can verify that answer, right? Which is out of those 100 samples, they exactly know which of these trajectories, because they are going to predict the entire solution followed by the answer, right? So it's going to verbose, it's going to like think through all the solutions, arrive at the final answer. Maybe it can think through different paths, right, to arrive at the final answer. So they're going to sample and figure out how many of these samples actually yielded the right answer, right? And what they say is maybe we can use that to better train a verifier model, which is, let's assume that I have a lot of compute with me, right? I'm not worried about like how many times I'm going to call the LLM before arriving at the right answer, but my focus is more like I want the right answer, even if it costs a lot. So what they say is that if you sample a lot of examples and then give it to a verifier, let's assume you have a good verifier with you, and the verifier can tell you which is the right answer, we are more likely to get right answers. That was their hypothesis. And to train a model, what they did was, like I mentioned, they took this particular checkpoint around, I think 2 epochs or something is what they took, and then they sampled 100 each for each 8K examples that they had. And of course, you will be able to, using deterministic techniques, verify whether the final answer is right or not, right? Because just an integer. So they would have, okay, for this question and for this solution, this was right. For this question, for this solution, it was wrong, right? So they will be able to get the labels as well. So what they did was they trained a verifier, which is again an LLM. They use the same autoregressive model, but rather than like in the final prediction layer, after the logics, they don't do a projection, but rather they insert a head, which will classify whether that particular whole solution, give the query and the solution is right or not. Is it, does it make sense, right? So basically the verifier would give you a probability of how good this particular solution is. And when you say, when you have 100 different solutions, you pass each of them through your trained verifier, and that verifier will be able to pick the one that is best at the moment, right? So this is typically called best of n sampling, which is in the current terminology, this is called test time scaling, right? If you don't worry about compute during test time, then you can do test time scaling, where you can with higher temperature, you can generate multiple samples, and then you can pick the best one from that, right? So this was the first paper that sort of introduced test time scaling. Okay, so let's see how adding the verifier into the pipeline helps, right? So what they say is that if you had a verifier to your pipeline, right, then you can see that the numbers jumps till 55% with 8,000 training data points, right? So now it sort of looks like with some more data, you can achieve good numbers much easier than what you would do with just fine tuning, right? So there are a bunch of more things also this paper talks about on how to make it more efficient. But the crux is this point that the paper showed how tools can be used during the fine tuning process, right? And these tools are non-differentiable, so they gave a nice technique to get it to work in fine-tuning setup. And they also talked about verifiers, which at this point in time, there is a whole literature on test time scaling, but this was the first paper that sort of hinted towards this approach, right? Okay, so let's move on to the next technique, which is tool augmented language models. So in the GSM 8K setup, we just had one tool and we just had one task at hand, right? So in this particular paper, it's slightly one level of abstraction above GSM 8K. What they say is that, let's assume that in addition to, let's say, Python interpreter or calculator, you also have web search tool or a machine translation tool, right? So let's assume that you have a bunch of tools available with you, and the LLM is allowed to use any of these tools in it during the response generation, right? So which means that it is not restricted to only one type of task. You're not fine-tuning it only for one type of task, but rather you have like 5 or 6 different tasks in your training data, and for each task you can use different tools, right? So they slightly abstracted out the same philosophy in GSM 8K. What they said is that the model, once it gets the input, will first figure out whether it needs a tool or not, and if it needs, what tool it needs, right? So for example, if the input is a machine is like a translation task, okay, so then probably it would say I want a translator tool. If it is a math word solving thing, right, then it would say I need a math tool or things like that, right? And then this is like the tool arguments, like what should you pass as arguments to the tools. And then once you predict all the arguments to the tools, then of course the model will say this token, which is now I want the result, right? So then whatever tool you picked would be executed, and the results will be appended here along with this token called output. And at this moment, again, the model will start to generate the next tokens, right? So this is clear. It's just the same thing as GSM-8K. It's just one level of abstraction higher, right? Like some examples are for math QA, you give the entire question, right? It's not going to do step by step in this place. You give the entire question, and then it says that there is a tool called formula, and this is how I want you to call the tool, right? And then once it says that and says the word like predicts the token result, then that will be executed, and then finally this will be added to the input, and then the model will predict the next token, which again is, and this for this setup it's exactly same as what the output was, but in other cases it might be different, right? In this is another example of natural questions where the question is where are hops added in the brewing process. So then the model decided that it's not in its parametric knowledge to answer this question, so it needs to use a search tool, and this would be the parameters for the search, which is the search query, and then the result of it will get appended here, and finally the model predicts the output. So here the output is not exactly same as the result, but it's just a small subset of it. So this was just one level of abstraction above, right? So there is no big novelty into it except for setting the problem in a good way. But what was important to see here is that in GSM-8K, you had to collect 8.5K examples for solving just one task. Okay, and the amount of effort that goes into that is insane, because you'll have to train people to sort of create a good data set. You have to express them. I need diversity. Expressing diversity is not an easy task, right? Expressing it probably is an easy task, but enforcing diversity is a very difficult task, right? So imagine that you have to scale it for like all the tools you want to use, right? So that's going to be insane. So what they claimed in this paper was that we will help you by coming up with an algorithm which needs very less amount of training data than what people in the past had used, right? So that was the big sell of this paper. So let's say that typically for fine tuning, you will have examples of one or multiple tasks, right? Which is the XS here could be math word problem, and Ys could be the actual solution for it. Or similarly for the QA, like natural questions, you might have a natural language question and an answer, right? So those are typically the task that you have at hand. And what they say is that for a small subset D for each tool, right? You create the tool annotations and the results, right? Not for everything, just for a very small subset, right? And what they say is that let's do R rounds of training or R rounds of fine tuning. And each round, what do we do? First, use the data set that you have and then fine tune the LLM, right? So the model will start to learn some aspects of what our tools are available, how to fill arguments, right? So because it's a very small subset, it might have not learned very well on how to use the tool, but it might have some ability to predict what tools to use, and some hints about how to use them. May not be 100% right. And what they say is that for every example that you have, right, it doesn't matter if it's in this D set or not in the D set, for every examples you have, just like how in GSM-8K you sample 100 with higher temperature, here too they sample with a higher temperature a large number of samples, and for that they call it N, right? So let's say N is 100. Okay, for that same input they sample 100 different tools, right? And once you have 100 different tool predictions, then you will be able to execute them and get the tool response, right? And then given the input, the tool prediction, the tool response, you will be able to predict the final output, right? So they check how good is that final output. If the output is good, they augment this output into the training data so that it will be used in the next round of training, right? So the whatever verifier did there, like they are using that strategy to bootstrap the training process, right? So the ideas are derived from there, but it's slightly different way of using Because here you don't need a verifier, right? Because this is the training data, so you have the output, like you mentioned, you'll be able to use a calculator and show whether it's good or not. So they are slowly sampling good data points and then bootstrapping the training. So let's say that you have level 1 complexity data points annotated. So maybe if you learn all level 1, maybe you will be able to solve a little bit of level 2, right? And then put the level 2 back into the training, and then slowly it sort of builds upon its own expertise, building step by step, and that's why it's called self-play algorithm, to improve tool calling abilities, right? So here, yeah, it was a very simple experiment where they show that for different sizes of large language models, here there's 220 million parameters and 3 billion parameters. What they say is that after we fine-tuned it using the proposed technique that they have, that they are able to achieve 30 points improvement across different sizes, right? So again, like the issue here is that in this technique is that, again, the number of tools are always fixed. Like how can you expand this to enterprise setup? Like you will have, like, say 20 different tools in your new enterprise. Again, you'll have to annotate. Again, you'll have to fine tune an LLM. And maybe it's not easy to verify the answer, right? So this issue of using tools is still there. You cannot generalize very easily. And again, they show one issue here, which is they say that for natural questions, 150 demonstrations was what that is needed to sort of learn a good model. But for math QA, they need 2K demonstrations, right? So the more complex your argument extraction and your tool chaining becomes, the more data you need, right? So while they don't need 8K, but still they need good amount, right? So it's a reduction, but it's not to a level where it's like easy, like I give me 2-3 examples, I'll be able to get it work, right? So it still requires a lot of effort. And again, the number of tools is also very fixed. Once you fine tune the model, you can't introduce a new tool, right? Or if you have to add a new tool, you have to retrain from scratch again, right? So those issues still exist. Yeah, so it cannot generalize to new tools, and it requires human annotations, right? So, because getting question answers may be easier, but getting that annotations of tool is what is very painful, right? Because you define the space of tools, you define how it has to be formulated, so that is a little tricky. So then there was another approach which said, like, let me help generalize it a little bit, and I will use lot lesser examples than what TALM paper used, right? So what they rely on is something similar to, so let's say that, so I think Tanmay already has covered chain of thought in one of his lectures before, right? Which is like normal prompting is that you give the question and you ask the model to give the answer right away, right? Chain of thought prompting is like you ask the model to think through the solution in a very verbose manner, and then finally arrive at the answer, right? And there are papers like Wei et al. Showed that chain of thought gives you a lot better numbers. And also there are multiple different ways of doing chain of thought. This is just an example to show that typically how people solve math word problems if they don't have a specific fine-tuned model. Like if you only have access to GPT-3 or GPT-5, ideally rather than asking to generate the answer, you should ask it to do chain of thought and then answer, right? So this was at that point in time for math word problems or logical problems or any other problems that requires reasoning. The accepted baseline was like you make it do chain of thought and then you arrive at the answer and the numbers will be good, right? So what this program-aided language model said, or the premise why they wrote this paper was that at that point in time, code models were pretty good, right? And these code models were good at Python, good at multiple different programming languages, Python being the most popular at that point in time. So there were a lot of benchmarks like most basic Python programming or advanced Python programming. There are a lot of benchmarks that shows models' ability to do Python programming. And code models did insanely good on even advanced Python programming. So what they thought was, look, most math and logical operations requires something like a programming language, right? So if you have access, if you're good at programming language, right, and you can convert all your logical and math problem into programming language, then why can't we use that, right? So that seemed like a slightly more generic solution than using calculator, wherein you predefined what all operations are supported and things like that, right? So if LLMs know most of what Python can do, that space is huge, right? So the crux of this paper is that don't do chain of thought by words, right? But rather try to express your chain of thought like a Python program. Maybe use natural language, but like sort of use natural language as comments in Python programs, right? So you will be allowed to think in natural language, which get commented when you run it on the compiler. but the compiler will be able to execute the instructions in the code, right? So that was their crux. And what they said is, we are also going to do chain of thought, because chain of thought requires 1 or 2 examples in the prompt, right? Few short examples, and then it will be able to generalize very well. So what they said is, if you have a problem at hand, then give us just 2-3 examples, express the chain of thought in Python. That's the only difference, right? And comment out natural languages so that it doesn't get executed, and then just run the code, and you will be able, once you run the code, get the answer and show it to the LLM, and then let it generate the final answer, right? That was the crux of this paper. And yeah, so similarly, so this is an example where this is the one-shot example they gave for this problem, how it should solve. Assume that there are comments here, right, in Python. In all the non-highlighted, in the blue highlighted one, assume they are Python comments, right? So it thinks through, it uses Python assignments, and then it uses variables, and then it creates a code for arriving at the final answer. Similarly, when you gave it the new question, it's able to exactly mimic how the example was given. But after this, this part is where the Python interpreter executes it and gives you the final answer 74, and then use the final answer as is. Because it's a math word problem, you don't necessarily have to call LLM again, because the Python program tells you like everything is in the final answer. So similarly, this is an example of a logical operation where while creating the Python program, the model makes some logical decisions, right? For example, the question here is, I have a chair, 2 potatoes, a cauliflower, a lettuce head, 2 tables, a cabbage, 2 onions, and 3 fridges. How many vegetables do I have, right? So this part is where reasoning comes into picture, which is when it creates the vegetables to count dictionary, it clearly excludes everything that's not a vegetable, right? There's no table, there's no chair, and there's no fridge, right? So so this is the part where reasoning comes into picture, logical reasoning, and then post that it's simple code, right? So what they say is that this can work for problems like these as well, right? Again, the big issue is that for every type of task that you have at hand, you have to give few short examples, right? Even though it can generalize to everything in Python, but still you need to understand what problem you can solve, and you need to define few short examples, which is a lot cheaper than what you would do for fine tuning, because there's no fine tuning needed, right? You can use any LLMs, you can just design a new prompt, and then figure out what prompt to use at the input, and then switch to that, right? So there is no retraining expense here, right? In TALM, if you have to add a new tool, you have to add a lot of data, you have to annotate the data, again fine tune the model from scratch with the new tool, right? But here you don't have. But the only flip side compared to TALM is that it can only work for Python, right?
Only tool it can use,
Or any programming language.
but it cannot use any other tool like TLM was.
No, it cannot. Right? Of course, you can't do web search, right? Because that's not the. So that's why it's called program-aided language models. Anything that is program-aided, it can solve, right? Right? So in the interest of time, I'll just skip this. But basically, it says that compared to chain of thought, PAL is better. But one good thing about this is that they said that for GSM 8K, the numbers on COT, it's not that small to begin with. It's quite high. And they show that this is because LLMs at that point in time have memorized single-digit arithmetics, right? And almost a little more than 50% of GSM 8K data was only single-digit arithmetic, right? So they say that I will systematically create a hard version where I will replace single digits with like 6-digit, 7-digit number, and then they show that the performance drops drastically, whereas the performance of program-aided language did not drop that much, right? So it shows better generalization and so on. Okay, so now let's move on to the next approach, which was slightly different compared to these approaches. Why are they different? Because these approaches only work in fine-tuning stage, and the task on which you want to use tools is fixed, right? You need to have data sets of that task. So let's assume you have huge Wikipedia corpus, right? And you don't have any task-specific corpus. Then it cannot work, right? Let's assume you trained for calculator for one particular task. Now let's say you use another task, right, which also needs calculator. Maybe it cannot scale. It cannot work for the other task as well, right? So Toolformer was a paper that helped solve the task problem. Like, first of all, you don't need task-based data to learn tools, right? And then they say that if you learn my tools in a non-task specific manner, during test time, if you give tasks that the model has not seen during train, it will still work. Of course, they don't say that it will work for new tools it has not seen during train. All they say is that it is task agnostic, right? This is one step towards what we really want. So what they say is we will fix the set of tools that the model will use, which is a QA system, which can use the web and things like that. Search system, web search, calculator or a math tool, calendar, and translation system. Okay. So what they say is, let's say you take a news corpus or something, right? And the news corpus says that out of 1,400 participants, 400 or 29% pass the test, right? So here what they say is, rather than just predicting 29% from the model's parametric knowledge, it may be better if the model says that, look, if I know that I want to predict the percentage of what I just mentioned before as the next token. So let me not predict it by myself. I will say that I want to use calculator at the moment for computing 400 divided by 1,400, and then let it give me the result, and based on that result I'll predict the next token, right? So this is not a very specific task, it's just like a sentence prediction, right? So similarly they say that the name derives from La Tortuga, the Spanish word for something, right? So at this point in time it knows that it needs a Spanish, like you need to translate this word to Spanish. So, sorry, this Spanish word to English, right? So maybe it's better to use a translator, get the output of the translator, and then decide what should be my next word, right? That will increase the correctness by quite a bit. So on, they show examples of other data sets as well. Like, for example, the Brown Act is California's law. You know that you're going to talk about the Brown Act later on, right? So if you can search the web, get information about Brown Act, then maybe you will be able to do a much better job, right? So this is what they want to achieve. Let's say how they achieve without humans having to annotate a lot of them, right? So basically what the model should do is, before the next word prediction, it has to figure out if it has to use tools, it has to figure out what tool should use, it has to figure out for that tool what all parameters have to be given, and finally once the results are there, it should be able to leverage the results to do the next token prediction, right? So for their experiments, they simply used unstructured, like normal text corpora, like no task specific data, no instruction fine tuning data, just normal pre-training data, which I think the data was some part of a news corpus, and then they used GPT-J, one of the open models at that point in time in 2023. So what they said is, they somehow want to annotate simple text with tools, right? So if you have a text like this, then they want to annotate that before I predict the steel city, I want to call a QA system which tells me what other name is Pittsburgh known by, and then once it gets the answer, I want to predict steel city. So somebody has to annotate this, right? So let's see how they end up annotating them in a systematic manner. Okay. First, what they say is that I will use a simple in-context learning prompt, right? I will tell the model this instruction, an LLM, this instruction saying like your task is to add calls to a question answering API to a piece of text. For example, Joe Biden was born in Scranton, Pennsylvania. It shows that you should probably say after in that where was Joe Biden born, and after that you predict the answer Scranton, right? That's what it wants to annotate. So they just gave an in-context example, and then they said for the corpus that they have at hand, they will go through paragraph by paragraph, annotate them with this, and that's their first step. Of course, it's going to be extremely noisy, right? It's going to be extremely noisy. You have to filter something, but the first goal is, let me cover as much as QA as possible, or as much as calculator as possible, as much as translator as possible everywhere, and now I'll filter what are useful. Then they said, execute them. Okay, so now you've figured out that these questions are possible. Execute all questions. Okay, and once you execute, you will end up getting the results. Let's say for this particular example, you have annotated in 3 different ways. right? Maybe they wanted to generate for every paragraph 100 different ways, right? So then you execute them, you will get different answers, right? So now is the filtering part. Now what they say is that let's see whether this execution actually helped me do a better job or not, right? So how did they do that? First is that let's compute the negative log likelihood of the word that is to be predicted after that, which is this part, right? The steel city, or just the like an average of that. So if I am given access to these executions, how does this prediction change? That's what they want to see, right? So what they say is that this is what they want to predict, right? The prefix here will include the tool call and the tool execution, right? So they say that without API call, I'm getting 2.5. This is a high number, right? And if I only give the paraphrased question, no execution results. Okay, just okay, I need to use the QA tool and I want this question to be answered. Sometimes it helps, sometimes it doesn't help, right? So the cases where it helps is like maybe during Viva, if the professor asks the question in a certain way, maybe you did not comprehend it well, right? But when they rephrase the question, maybe sometimes it clicks, right? So it may so happen just by rephrasing the question, the model figured out what the answer was, right? And it was able to do a good job. So what they do is model's inherent ability to know that knowledge is a min of these two, right? It's just the same question rephrased in a different way, right? So that is the one part. Now, given the answer, how does the log likelihood change, or how does the negative log likelihood drop? If there is a drop, then the answer helped. If there is no drop, then the answer did not help. In fact, it confused the model, right? So whenever there is a drop, those are good candidates. And whenever there is no drop, they will skip those candidates, right? So ideally what would happen if this was there, it would have probably made no sense for Scranton. Sorry, Steel City. This might have helped, and we don't know whether this helped or not, right? So what they say is that I will use these techniques to identify good candidates and then use them for my training process, right? So without actually annotating the dialogues, just with few short examples, they got tool annotations, and then they used a technique to filter them, right? And then finally they show on different tasks. So fact completion, question answering, maybe web search and Wikipedia search, right? Math is calculator, temporal requires calendar, multilingual requires a translation tool. So what they say is like, this is the GPT-J model, the light blue one. The dark blue one is a Toolformer trained with the tool, right? And this was the state-of-the-art model back then, GPT-2, right? So they say that for almost all tasks except QA, Toolformer, which is just a 6 billion model, was able to beat GPT-3, 175 billion model. Of course, for math, it will be obvious for you guys now, right? Because anyway, GPT-3 was very bad at math. Temporal reasoning also, it was really bad. It was even worse than GPT-J for some reason at that point in time, right? Same thing with multilingual. Now, this part is because for question answering, it was basically Wikipedia-based things, and GPT is good at language. It has memorized the whole Wikipedia, right? So that's why they're not able to get better numbers than that. So the summary of this paper is that it's not task specific. The solution is slightly more general purpose. It can scale to tasks that it has not seen during train, because it just happens in next word prediction, right? And it requires very few human annotations, because you just need those for every tool that you use. You need a few short example, and then she'll be able to annotate and get the whole data by itself. And again, the biggest problem still lies, which is all these techniques cannot generalize to tools that are unseen during train, which means that if you are like GPT folks at that point in time might have already trained for search and calculator and things, and so they would be able to do a good job there. But still, if you want to develop your own agentic autonomous system using APIs that are available to you, you still don't know how to do it, right? So in the interest of time, I'll probably pause here. Maybe if I have time in the next lecture, I'll cover WebGPT. But yeah, so this is the landscape where people did not know how to extend it to tools that were unseen during train. Okay. And in the next class, we'll talk about how did LLMs get the ability to use any tool that was given to it during testing. Okay, thank you.